thanks so much for having us. My name is David, and I'm indeed here with Kareem. And we thought we'd share with you what our experience has been like over the past year deploying Kubernetes in an educational context. I happen to teach a course at Harvard called CS50, or Computer Science 50, which is our introductory course in computer science. Happens to be Harvard's largest course right now, with about 800 students on campus. And we also collaborate with a few other campuses, Yale among them, where we have 200 students. And we also take part in the school's continuing education program. So we have adults as well, both on campus and off online. So in total, everything actually, rather, that you'll see today can be seen for free at edx.org/CS50, because everything we've been doing for the past 13 years has also been freely available as OpenCourseWare. And as a result of that, have we had some challenges of scale, not just with the 1,000+ students we have on campus, but with the tens of thousands that we have online as well. So indeed, this is a map that depicts some of the communities that this course has built up over the past few years. Red dots represent high schools, blue dots represent universities and nonprofits who have been adapting or adopting the course in some form and using its curriculum and, in turn, its tools to teach computer science locally, so that the course is not strictly a MOOC or massive open online course. It really is a curriculum that others have adapted for their own purposes in local in-person communities. So in Cambridge, Massachusetts, we have about 1,000 students on campus, and online, we have, through edX and other channels, we're told over 1 million registrants to date. Not everyone participates on a daily basis, but in a typical period, we would have 30,000 students participating actively, banging on the infrastructure all at one time. And so this has motivated some creative solutions and certainly some struggles with challenges over the past couple of years in dealing with that many students. But it all started in Cambridge, Massachusetts, little old Harvard Yard, some 30 years ago when we started this course, even before my time, just having an on-campus cluster, a bunch of Unix systems that were interconnected on campus. Students had a home directory. They had a shell account, username and password. NFS shared everything. So they would telnet in, back in the day, or now SSH into this cluster where they would write their programs. The course happens to be primarily in C, followed by a bit of Python at the end of the semester. So the first things students are using are GCC, or now Clang, GDB, and other command line tools. The picture that they see when they log in is just this, a black and white interactive terminal with which you might be familiar. And topologically, what we implemented, or rather what Harvard had implemented, was some load balancer that routed traffic across a bunch of systems there. But unfortunately, because Harvard, the university, was running this, we didn't have administrative or sudo access as the instructors. This made it hard to maintain the latest versions of software that we wanted. It made it impossible for us to see in situ students' code as by becoming them. And therefore, helping students in this architecture was never really ideal. And so when AWS and the cloud started to become a thing some 10 or so years ago, did we start to experiment with AWS at the time. And at the time, there was not the crazy long menu of services. There was pretty much just EC2 and a couple of other things. And so we had to build ourselves using virtual machines, that same topology, but in the cloud. And we did this for a few years. The picture ended up being pretty much exactly the same, but it was all now cloud-based. And we replicated the architecture we knew well. The upsides were we had all of the features we always wanted. The downsides were that we suddenly realized we were now our own system administrators, which was not without its challenges as well. Human costs, particularly since our primary goal is to teach, not necessarily to administer. So over time, we considered other possibilities. And we evolved ultimately for several years into what we call the CS50 Appliance, a downloadable virtual machine running Fedora initially, then Ubuntu, that students could run on their own Macs and PCs. But this was primarily motivated by our OpenCourseWare initiatives. Even though we'd made all of the course's assignments and lectures and videos and PDFs and everything freely available for years, it was still a pretty passive experience for many years. Students could try to figure out on their own Macs and PCs how to replicate this Linux or Unix-like environment that Harvard students had access to, but we just weren't in a position 10 years ago to give everyone shell accounts, or strangers, no less, shell accounts on the internet to do with it as they see fit. So we instead did this client-side thing so that they would have an identical environment, but completely sandboxed locally. This, of course, too, was not without its challenges, but it did give us a nice graphical user interface, still with a terminal window, code editor, and the like. So it was a little more user-friendly. But technical challenges were, frankly, more costly than we had hoped. Stupid things, too. Networking adapters on Windows not quite working between the virtual host and the local machine, and other sort of headaches like that, where now suddenly we weren't administering server-side architecture, but now we had hundreds or thousands of students emailing us or posting online that they're having some other issue with the architecture that had nothing to do with the curriculum or computer science per se, really just the plumbing that we were using at the time. And so then in 2015 and since, have we used introduce this a cloud-based IDE, what we call CS50 IDE, which it can be used by anyone with a free GitHub account at this URL here. And when anyone logs into this account now, they see pretty much that same environment. A code editor up at top, tabbed interface and the like. Down below, they have a terminal window. So our goal, to be clear, was not to have a sort of playground type environment for programming, but we wanted this cloud-based environment to be as representative of what they might use in the real world on their own machines. And then a file browser here at left. But there's a number of more pedagogically and software engineering features as well. On the right-hand side is a collaborative window where they can chat if they're doing peer programming, or if we have a student halfway across the world, can we chat with them interactively? Along the top, if they enable it, is a version history. So in addition to any command line tools like Git and the like, they can literally just scroll back and forth in time, which is much more accessible to new programmers. On the right-hand side, thanks to our team and Kareem, there's a graphical debugger. Underneath the hood, it's still using GDB, but it wonderfully lets students see their stack and variables and so forth, so a lot more user-friendly, certainly in the earliest weeks of the class. And all of this is thanks to what was previously a startup, Cloud9, some friends of ours there with an open source SDK, on top of which we started building these educationally themed JavaScript-based plugins. More recently was Cloud9 acquired by Amazon, at which point it became an Amazon service, but the back end, by default on Amazon, assumes EC2 instances, or virtual machines, which, as we'll tell, was not necessarily ideal for us. And so along the way, have we tried to build out essentially a solution to two problems, the file browser at left, the terminal window at bottom, so that all students have the illusion of their own server in the cloud, but to do this as economically efficiently as possible, as human efficiently as possible. And for that part of the story, allow me to introduce my friend and colleague, Kareem, to take us through our experience.
All right, thank you so much, David. So among the reasons why we chose Cloud9 early on was that it was nicely extensible in a way that allows us to easily customize and extends the user interface and user experience to make it hopefully more accessible to students who are first sort of encountering something like this. The other reason that we chose Cloud9 was that it was backed by Docker, which meant all what we needed to do is maintain a Docker image. That we would bake in our tools and our languages, our packages and configurations into it, and that was it. So students would go to something like c9.io or cs50.io and create their account or log in and then be presented with their IDE. Now, after the acquisition by AWS to Cloud9, they decided to change this model a bit. And so they decided to back the compute environments of this Cloud9 IDE that we saw a moment ago by EC2 instances that would live in users' accounts. Now, I could see at least two reasons why this is not ideal for our use case. The first reason is that the AWS console is not really sort of intuitive to most people who are using this for the first time. And the second reason is that in some, if not all instances, to create an AWS account, you need a credit card, and that's not easily accessible for students, let alone students abroad as well. And so, as I mentioned, there's the Cloud9 IDE that we saw a moment ago with the text editor, the terminal emulator, the file browser, and so on and so forth. And this is backed by some compute resource where the actual programs run or where the actual files are stored. And the Cloud9 IDE connects to this compute resource using the SSH protocol. Now, by default, in case of Cloud9, this compute resource happens to be an EC2 instance. And so what we ended up doing really is, since Cloud9 decided to stop doing orchestration, is we had to implement the orchestration on our own. And so the straightforward approach that we went to was to use EC2 as well for orchestration. So we wrote our own simple orchestration tool that orchestrates EC2 instances and uses EBS volumes to persist students' files and folders. So things like their assignment files and project files and so on and so forth. And so we started out by having a warm pool of EC2 instances in one availability zone, and this is just to make things faster in order not to wait for the EC2 instance to start in order to connect the IDE to it. But of course, there's more than one availability zone in each region, and there's even more than one region that we want to operate from within. And so you can imagine that this got pretty complicated pretty quickly. But here are some of the steps that we would do in order to create an IDE or redirect a user to an IDE once they visit IDE.cs50.io. We would first get an available EC2 instance from the pool. We would create the user's EBS volume, attach it to the EC2 instance, format it, create a file system on it, mount the volume on the instance, start the Docker container, mount the volume on the Docker container, expose some of the ports, connect the IDE to the container that's running on the instance, and then finally redirect the user to the IDE. And so just to have an idea, here's the diagram that represents how this would look like. So we have the Cloud9 IDE front end connected to the container using SSH, which is quite unusual, I know, through the EC2 instance, and then we have the EBS volume that persists students' files and folders. And so what are some of the challenges that we had with this approach for compute? Well, first of all, we had to maintain pools of EC2 instances across availability zones and regions, which was quite complicated. So we had to worry about things like race conditions, not assigning the same instance to two users if they log in at once, or like if some instance terminated expectedly or unexpectedly, we had to ensure that the capacity is still the same. We had to get down to the level of using SSM, which is another Amazon Web Services that's used to run commands remotely in EC2 instances to do things like starting the Docker container and so on and so forth. We had to allocate an entire EC2 instance for each user, even if the user does not really need the entire EC2 instance for the purpose of the course, does not need the entire amount of resources that's on the instance. After the session ends, we had to do some cleaning up. We had to terminate the instance. We had to wait until the EBS volume that persisted students' files is detached. And that made things quite slow. If the user comes back immediately, they had to wait for a bit. Since we terminate the instance after each session, when the user comes back again, they would get a new instance with a different host name, which made things a bit complicated in terms of the SSH connection, because now the SSH parameters are different, and also students working on web projects inside of their IDEs, they would get a different host name every session, which was quite annoying. We had to remove the instances temporarily from the pool to optimize for the storage on the instance to update the Docker image on this instance. All right. These are also some of the challenges that we had with EBS for persisting students' files. So for the same reason, we also had to allocate an entire EBS volume for each user, which wasn't quite cost effective because it's not necessarily the case that the user is going to use the entire space on this EBS volume. And we had to assign each user a specific availability zone. And this is just a limitation of how EBS and EC2 work together, which meant that even if there was an instance available in the region, but in a different availability zone, we could not assign it to the user because the EC2 instance and the EBS volume had to be in the same availability zone. OK, so we'll come back to the compute challenges in a moment. But in an attempt to solve some of the storage challenges, we tried out S3 instead. So we would create a prefix or a folder on S3, for each user, and then give each user read and write access to this prefix and folder. And then when the user would come in, we would download their data and then upload it periodically. So here's a diagram that represents something like this, pretty similar to the previous diagram, except instead of EBS, we use S3. And so what are some of the challenges that we had with this S3 approach? Well, since we're creating separate folders for each user, and we're granting them read and write access in this folder, we had to set up some sort of credentials to grant them this access. And we had to refresh those credentials between sessions as well, which added a lot of complexity. We had to download the data initially, like I said, and upload it periodically to sync the data up. And then there was no really, by design, S3 was really designed to be elastic. So there was not really a clean, easy way to sort of limit how much a user can store in their folder. OK, so we started considering other orchestration tool. Among them was AWS Fargate, which is another orchestration service that's offered by AWS. But unfortunately, one of the limitations that Fargate has is that it doesn't have image caching, which would have slowed things a lot down for us when it comes to starting the IDE, because you need to wait until the image is pulled first. It also didn't have persistent volumes, so we could not really easily persist data on AWS Fargate. We also considered AWS ECS, which is another orchestration service provided by AWS, but we were actually using ECS for another application at the time. And one of the limitations that we noticed with ECS is that if you have more than 3 tasks that are running at the same time, starting more tasks or starting newer tasks seems to take a lot longer, which wouldn't play nicely in our use case. And then finally, we considered Kubernetes for orchestration. And so these are some of the steps that we would follow right now to create a user's IDE. So we create a namespace per user. We create a persistent volume claim to request some storage to persist the student's files and folders. We create a single container pod, mount the PVC on it, mount the public SSH key to establish a SSH connection. We connect the IDE to the container, and then we redirect the user to the IDE. So here are some of the solutions. Here are some of the solutions to some of the challenges that we encountered that Kubernetes helped us with. So previously, we had to maintain pools of EC2 instances, like I mentioned. But now, Kubernetes really manages the nodes for us with little to no interference from us at all with the management of these nodes. We used to get down to the level of running SSM commands to do things like starting a Docker container and such. And now we just nicely use the Kubernetes API to do that in an abstract way for us. We used to allocate an entire EC2 instance for each user, but now we're able to actually run multiple containers on the same instance and share the resources among these containers, which is nice. We used to do the cleaning up step, terminating the instance, waiting for the volume to detach, and now we just kill the container. We used to get a new different host name per user, and now we use some core DNS configurations plus some reverse proxy that we have deployed to resolve some host names to private IP addresses within our clusters to the containers, the IDE containers. We used to remove the instances temporarily from the pool to update the Docker image, but now we actually use a Kubernetes resource called the daemon set to basically pull the image on every worker node that we have pretty easily. OK, now for storage challenges, we use a tool called Portworks. And Portworks, if you're not familiar, is a storage platform for Kubernetes that abstracts away EBS, a bunch of EBS volumes, and gives us basically a storage pool that we can allocate volumes from. And so Portworks also has a feature called Cloud Snaps that allows us to archive some of the volumes to S3 for when we use this for archiving purposes, snapshotting purposes, or for optimizing the storage capacity that we have, optimizing use of the storage capacity that we have. And so here are some of the challenges that we faced with EBS before and how Portworks helped us solve these challenges. So we used to provision an entire EBS volume for each user, but now Portworks helps us actually thinly provision this storage. So it's not necessarily that you say, I want a 1 GB volume, that you're necessarily taking 1 GB from the capacity until the user is actually using the 1 GB. And we also take snapshots to S3, like I mentioned. We used to assign availability zones to each user. But now Portworks actually manages the EBS volumes for us and manages the provisioning of EBS volume as well. So we don't really have to care about that. With the S3 approach, we used to do things like set up and refresh the credentials, download and upload user data, and there was no easy way to limit the size. But now Portworks actually allows us to do that. So simply by specifying the size in the PVC, we get a volume of maximum size, and we don't really have to worry about any of the challenges above. And so here is another diagram. So we have the container running on a worker node instead of the cluster, and the IDE connecting the container using SSH. And then we simply rely on Portworks for persisting students' files and folders. And so one takeaway here from this is that we're kind of using Kubernetes and Portworks and maybe even Docker in an unusual way. But this is a graph from our Google Analytics dashboard, and it shows the activity of how many sessions we get per day. And as you can see, since the start of the semester, we get about 8,000 to 8,500 users per day. And this solution seems to be working well so far. Here's some of the future work that we have. Since this is a freely available tool for anyone online, some people actually misuse this tool for things like crypto mining or DDoSing some remote hosts or sending spam email. And we try to do our best to minimize some of these activities and prevent them, but it's not an easy challenge, as you may know. We also want to have multiple clusters in the same maybe region or available in the same regions, or even maybe even in different regions. And we want to be able to give multiple IDEs for each user to simply use different IDEs for different courses, or maybe even based on different Docker images. And so yeah, that was it. I highly encourage you to go give the IDE a try at ide.cs50.io and give us some feedback. And we're going to stick around for questions. And if you want to reach out to us, there's our emails right there. Thank you so much. So the question is, what made us go with Portworks? We looked into other solutions, like I said. Like we tried EBS, we tried S3, that didn't work out quite well. We tried very briefly StorageOS as well. It wasn't as easy to get started with. And so Portworks seemed to be pretty popular, seemed to have a good community around it, and they have been amazing support-wise as well. Yes. Yes.
What does your entire storage size look like for the mass of what you're storing with Portworks?
That's a good question. We have Portworks. We have multiple. What's that? Oh, sorry. Repeat the question. So the question is, what does the maximum storage look like for us? So we have a bunch of EBS volumes that are provisioned and managed fully by Portworks for us. And I think the total size of these is something like maybe 10 terabytes or so, I think. I'm not quite sure, but we can resize this. We should be able to resize this pretty easily as we need. Good question. Yes?
Between version 1 and version 3, what was the impact to your actual cost to run the systems, as well as operation cost, monetary as well as operations?
That's a good question. So what was the impact of the operational cost as well as the monetary cost? I don't have exact numbers right here, but I can maybe speak more on the operational side of things. I highlighted some of the challenges that we had with the previous approach, some of the things that we had to worry about and implement. And now just using the Kubernetes API to create the resources that we need, it's just pretty straightforward. I don't have to worry about as many sort of low-level details. I don't have to worry about which instances has which resources available. Kubernetes manages all of that for us. So I think on the operational side of things, I think that cost was reduced significantly by using Kubernetes.
And if you drop us a note, we can try to give you some specific numbers. And the two axes along which it's reduced is, whereas previously every student would have one EC2 instance, albeit a small one, now we can run as many as 80 containers on one instance, granted a bigger container, so there's some wash there. Storage, though, even more compellingly, previously we could allocate a gigabyte per student minimally, and now we can do that much more thinly, as Kareem noted.
Yes. Your delivery is 7 by 24 around the clock. The intention is this at full time.
The question is the delivery 24/7? Yes.
For better or for worse? Yes.
Yes.
Are you using EKS?
The question is, are we using EKS? And the answer is yes, we are using EKS. Yes.
So what's the size of your cluster in that peak, and what challenges have you run into? I mean, it sounds beautifully, but I think we've all worked with Kubernetes. So what are the challenges you run into at that scale?
So the question is, what is the size of our cluster, and what are some of the challenges that we run into? The size of our cluster varies depending on
8,500 users for your.
Correct, yes. So that varies. Unfortunately, it varies manually, though. So we have to scale up and down manually right now. And the reason is because our compute cluster is the same cluster as the storage cluster, but we have one of the things on our to-do list is to basically isolate the storage cluster from the compute cluster to be able to dynamically scale up or down the compute cluster as we please. Yes.
Any reason why Cloud9 versus the Studio Code?
I'm sorry, can you repeat the question?
Why Cloud9 and not something like Visual Studio Code?
That's a great question. The question is, why Cloud9 and not something like VS Code? And the answer is that we've been actually using Cloud9 for a few years now. And so most of the extensions, most of the plugins, most of our ecosystem is actually built around Cloud9. And we also they give us good support as well.
And VS Code didn't really have as much momentum several years ago when we first started. We don't want to run software client side if we can avoid it. Just too many technical support headaches. We at least want to have an option for a cloud-based environment for new students. And it's recently now that there's like online.visualstudio.com, which is actually getting much closer to this kind of architecture. Unfortunately, that one too is still tied to an individual user's Microsoft account and credit card and the like, and there's not yet the abstraction that we could provide on top of that.
Yes.
Back to the credit card question. So in this solution, the student does not have to submit a credit card to begin. Is that solve that problem?
The question is, do students need credit card to sign into this? And the answer is no. All the students need to sign into this is really a GitHub account. GitHub account. Yes. Yes.
How many namespaces are you up to?
Wow. How many namespaces are we up to? I think we're something along like maybe 30, 40,000 now. And EKS, I think we struggle at some point, like we overwhelmed the the control plane at some point, and I think they had to scale something up for us.
So are you doing any deprovisioning with the namespaces? I assume.
Yes, we are planning to. Yeah, we are planning to basically sort of cluster these into different clusters, maybe in the same regions or different regions. Yes.
Do you guys handle connection failures, like underlying pod failures in the cluster? Like for a user, they have to take an action, like the pod were to be evicted from a node for one reason or another?
That's a good question. So the question is, do we handle connection failures or things like the pod getting evicted from the node for some reason or another? So we try to have enough capacity so that this doesn't happen or like happens at minimal. One of the reasons why this is really nice is that we also, it makes distributing managed update easier for us. And so what we do basically, is that if a pod gets terminated unexpectedly for some reason, it notifies the user on the front end with some error message or something, and the user can easily just get a new IDE by as easily as reloading the page or like clicking the retry button or whatever. And that gives them a new pod, a new container based on the new image, the latest image that we have, and that there's also a manual way to actually do that, to actually restart the container in order to get these updates as well. Yes?
Do you prioritize students over external customers or have separate pods, separate customers?
The question is, do we prioritize students over external customers? We're hoping, so we definitely give priority to students, and this is meant to be a very specific tool to be used with the class. And that has its upsides and downsides. One of the upsides that it has is that it gives us more flexibility in terms of what we sort of can enforce and implement in this environment because we have certain expectations. But the downside is that if you're a general purpose user and trying to use this environment, some of your changes might not persist, for example, or like you might not have enough resources as you please. But yeah, so ups and downs.
Sunday nights before the homework assignments are due at midnight, we prioritize the on-campus class.
Yes?
Are you planning to open source your solution so that others can also run this for you?
Sorry, can you repeat the question?
Are you planning to open source your solution so that others can also use this to run their own app?
So the question is, are we planning to open source our solution so that other people can use it? And I think the answer is yes. We just need to clean things up a bit. Yes?
Yes, I understood that. So is the code being auto-pushed to GitHub like as it's being entered, or what happens if the pod fails? Like what's like the same protocol?
Oh, okay.
Like do students have to actually push?
Right. So the question is, do students have to take any manual action to push their code somewhere? And the answer is no. Portworks, the storage platform that we're using, actually manages all of that for us and abstracts away all of these details. So if there's a write failure that happens, they do something on their end to retry this. And if there's something fatal, then obviously there might be some data loss. But students don't have to do anything manual to do that. Yes? Sorry, can you for the so we use the Kubernetes. So okay, what do we use to launch a new pod or deploy a new pod? Is that what you're saying? Okay. So we actually use the Python client for the Kubernetes API directly. So we have our backend at ide.cs50.io, and we simply use the API to start a new pod. As simple as that. We don't use any CI/CD pipelines.
Maybe one last question.
Okay, one last question. Yes?
If you're going to prioritize the parts that you want to open source from the courseware so that students and other universities can contribute to the environment and the IDE and the infrastructure for that, and how you deploy Kubernetes, of those three items, what are your priorities as far as looking at open source?
It's a good question. Pedagogically, the plugins are of great appeal. The question being, what would be our priorities in terms of open sourcing things? The catch is right now, Amazon's support for third-party plugins is still very nascent, and so they wouldn't necessarily yet be that useful, so I think we would nudge them down on the list. And then really, as Kareem says, we've been developing the back end really for internal use thus far. There's no reason it's not yet open source other than we need to document and clean up.
Thank you everyone for coming. Please go have fun in reception and don't forget to rate and give them